In general, static systems can be subjected to multiple loads. Newton's laws tell us that the sum of forces is important. Turns out the sum of moments is important too. Remember, when we add two vectors together, we call the new vector the resultant, and so a resultant moment vector is what comes from adding two moment vectors together. This video is going to show you three ways to add multiple moments together. We'll do this graphically using geometry or trig and vector components. So just a quick recap, this is all shown in another video about forces. It's the same thing now, it's just moment vectors instead of force vectors. When we add things graphically, we start by drawing ourselves a grid, position the vectors head to tail. The resultant moment is going to begin at the tail of the first vector and end at the head of the second. If this falls on a nice grid point, or if we have a ruler, we can find the resultant directly just by measuring. That's really nice. Second method would be to use geometry or trig. This has to do with positioning the vectors head to tail, and what we end up with is either a parallelogram or a triangle to solve. And so we use a couple of geometry tools here, such as the sum of internal angles for a triangle being 180 degrees, or for a parallelogram, it's 360 degrees. We also have the law of sines and the law of cosines at our disposal. The last method is breaking things into components and adding them together. So even though this is the most equation-oriented version, don't lose sight of the fact that you're still just positioning the vectors head to tail and then breaking the components up, because the resultant vector is just the sum of the components that formed it. Keep in mind, if you want to draw a star on something, this would be it. We have to find the individual moments first. Find individual moments first. And the reason for this is that depending on what location we decide to sum our moments about, the applied forces create individual moments, and we can't just add them together at the end. So just to give you a quick example here, let's imagine we have a little beam like this. The first thing we want to do is pick a spot to sum the moments about. Perhaps we'll pick this end here and call it point A. And if there were, say, 4 applied forces, one here, another going like this, one going like this, and one more going like this, we could call them, say, F1, F2, F3, and F4. We can see F1 goes right through point A, the line of action, and so it doesn't create a moment, but the other ones do, right? So we can look here and we could say, well, F2 acts at a distance that we'll call D2, F3 acts at a distance that we'll call D3, and F4 acts at a distance that we can call D4. And so we can find the moments one by one here, right? Moment caused by 1 about point A is going to be F1 times D1, but we said that that was 0, so this thing doesn't create one. However, F2 creates M2, so M2 looks like F2 D2. M3 is going to look like F3 times D3, and M4 will be F4 D4. From there, we could add these together, right? Sum of moments is going to be equal to M1 plus M2 plus M3 plus M4. And you couldn't have done that beforehand. You had to find the individual moments first. Remember, M1 was just 0. So the next thing I'd like to point out is that we need to be careful with signs. Not sign like the trig function, sign like positive or negative. Remember, we use the right-hand rule. Right-hand rule. And what that says is that positive goes with counterclockwise rotations and negative goes with clockwise. So in this example here, what we really have, well, we've got M1's equal to 0, M2 caused by F2, That F2 is causing a counterclockwise rotation about A, so that is positive, greater than 0 counterclockwise. M3, same story. Force 3 is trying to rotate us counterclockwise about location A, so that's also positive. But M4 is actually trying to rotate in the clockwise direction. So M4 is actually less than 0. It's negative clockwise. So we actually need to correct our summation here. Whoops, ran out of page. The correct way to do the sum of moments here would be that the sum of moments is equal to M2 plus M3 minus M4. Keep in mind we can also do this in vector form. Right, we had M1, oops, change colors here. M1 was equal to 0. Remember, moment vectors point in the direction of the rotation axis. So M2, in a 2D plane, it might feel weird, but the rotation axis is the third axis coming out of the page at us, right? So if we have X and Y like this, Z is coming straight out of the page towards you. That's the axis of rotation here. So M2 would have been something like F2 D2 times K hat. M3 is going to be something like F3 M3 will be something like F3 D3 times K hat. And M4 is going to be F4 D4 times negative K hat because it's rotating in the other direction, right? We tend to write this as just minus F4 D4 K hat, but I don't want you to get mixed up. The negative sign here came from the direction of the vector, not from the direction that F4 is pointing. And by the way, even though we could have just eyeballed this one, you could have gotten all of these using good old R cross F for each one of these if you worked it in vector form. Last thing that I'd like to tell you about this when it comes to finding resultants, here's a little trick we can do. We can actually place the resultant force so that it creates the same moment. So it creates same moment. Now, when we do this, we have to constrain ourselves. There's an infinite number of options here, but if we were to continue playing with this beam that we've been playing with, when we sum all the forces together, perhaps we end up with a force that looks like this. That's what happens when we add all those forces together. Well, we already decided that we were summing moments about location A, and we were able to find that just by doing the sum of moments about A. That's what we did on the last page. But we also know that the vertical component here, Fy, has a moment arm. We don't know what it is, but there it is, right? Some unknown distance d if we were to say that this force is applied along the beam. And so we could say that Fy times d is equal to that sum of moments. We could calculate both sides of this independently and solve that for d, right, as the sum of moments over that force, and we could find out what location the resultant force would have to act at. The reason I say there's an infinite number of options is the second we move it, right, if we put F here instead, now we have two unknowns. We have a vertical distance and a horizontal distance, and you could do that, right? R cross F, we could solve that, and we could do it again that way. Usually it's easier to pick and lock ourselves down in one direction and not the other. But this is a great little trick so that instead of having to have an applied moment, we can just pick a location, put the resultant force, and it has the overall same effect on the system as all those individual forces, including the moments that they caused.